Hello, once again. Addressing the issue of a viewer that asked a question about grounds in circuits, we have to understand a couple of things first. With the battery source that we start, regardless of the type of circuit that it is, we're going to have a ground. Why do we have to have a ground in the first place? Why can't the circuit be floating? The reason being we have to have a complete path. So if current flows from positive, this is a symbol for a battery. This is a different type of circuit as you see over here. The current will flow from the positive through this resistor, come out the other side, go in one side of this resistor, the 5 ohm, come out the other side, go back to ground. Now where is ground? Ground is here, going back to the other terminal of the battery. We have to have a complete path for the current to flow. Now, the problem with grounds is, especially with automotive, we're always hesitant or concerned about a ground having resistance. So the question was asked, how much should you measure from ground? How much should you measure from ground in a circuit, whether it's a fuel pump, whether it's a starter motor, whether it's a computer ground? How much should you measure? 1 volt, 2 volts, 3 volts? First, to answer these questions, we have to delve into the circuits itself. A regular circuit over here, if I have 12 volts and I have 2 resistors, let's say these are one bulb, this is another head bulb. If you go to the midpoint over here, you'll have 5 volts from here to here. That's taking into consideration that in between here and the ground, there is no resistance. There is 0 ohms resistance. From here to ground is 0 ohms. And this is the unit of measurement, ohms. Which brings us to, if I have 5 volts across here, how much do I have from here to here, the voltage drop? We have 7 volts over here across this resistor or this bulb. Let's do something different. The textbooks tells us, and as I always mention, this textbook over 20 years old. So you're going to say this theory is outdated. It has nothing to do with vehicles in the year 2021. What does it have to do with it? Okay, let's try something then. We just said from here to here there's 0 ohms. Why? There's no resistance. The textbook says no. A bad ground. What's a bad ground? After the 5 ohms, right? We're going to put in a 1 ohm resistor. They're going to say, what difference does it make to the circuit? Look at the difference. This from here to here with respect to ground was 5 volts. From here to here, across this resistor is 5 volts. Or this headlamp. Or this parking lamp. We threw in 1 ohm. That screwed up the circuit. Now the total resistance from here to ground, and I'm not going to get too technical with Ohm's law, has changed, has increased. The ohms resistance has increased the resistance. What does that mean? Less current. What does that mean across this? That means we have a voltage drop across this. Over here, from here to here, how much was the voltage drop in theory? 0 volts. That's what we want. With respect to after the load or after your last component, from here to ground, we should always get 0 volts. From here to here, guess what happened? Now we created a voltage drop, unwanted voltage drop, and unwanted resistance. There is 2 things in electronic theory. You want resistance, and sometimes you have unwanted resistance. What's wanted resistance? Wanted resistance is you have resistance. Why? To lower the current. We can't just put a battery without resistance because in theory, the current will be infinite high. We have to lower that current. There are 2 things. There's voltage, there's current. Current goes through the circuit. How do we control how much current? By putting in resistors, resistance in the circuit. But this is called unwanted resistance. We don't want this resistance here. We want this. From here to here is 0 ohm. So as we said, this upset the whole circuit. Now I had 5 volts from here to here. I was happy with that. Now, look what happened. I went up from 5 volts to 5.54 volts. Oh, let's say 5.5 volts. Why? What messed it up? What's the difference between here? A bad ground. 1 ohm. And you'll say, does it really make a difference, Joseph, if we measure 5 volts in the circuit or 5.5 volts? Does it really make a difference to a computer? Yes, it does. Everything makes a difference to a computer. So, this over here, we went up 0.54 volts because of this ground was introduced that gave us resistance. How does that apply to any automotive car with electronics in today's vehicle, in modern vehicle? Again, this textbook is over 20 years old, right? That means we don't have bad grounds anymore in automotive. Another question that was asked to me, and we'll get to answer this one. 12 volts over here, okay? This is a different type of circuit from the textbook, obviously. They draw it a little different, but I think you'll understand the point I'm trying to convey. If you have a fuse and you have a switch, this is the symbol for a switch. In this position, this one is making contact with this terminal. That means it is closed. So therefore, 12 volts across here. How much is the other side of this fuse? If this is 12 volts, how much should be the other side? Regardless of, you see there's no rating. There is no current rating in this example, in the textbook. Why? Because it doesn't make a difference how much current that fuse is rated at. Like we said, could be 10 amps, could be 20 amps, 30 amps, could be low as 7 amps, as low as 2 amps. Doesn't make a difference. 12 volts, 12 volts. And at the switch, how much do we have at the switch? Well, if they told you there's 12 volts across each one, why? Is this because we go back to Ohm's law? Is this a series circuit or is this a parallel circuit? This is a parallel circuit. Not only are you putting the voltmeter across in parallel, but the lights themselves are in parallel. They're across each other. All these, one side of these lights make contact to the same point of the switch. Where does the switch go to? The fuse. Where does the fuse go to? The battery, the positive side. So all these are connected to the same point. To the same point. All this is one point, the same point, the same point. Therefore, parallel law tells us across each circuit, in this case, it's a bulb, could be reverse lights, could be parking lights, could be any lights at all, any load over here. Could be a fuel pump, another fuel pump, another fuel pump, it does not matter. They are in parallel, 12 volts, 12 volts, 12 volts, across each one. Why do we do it in this way? Because if the circuit breaks, let's say this wire between here and here breaks for whatever reason, that's a break. What happens to these? Which one fuel pump will work? This one will work because it has a complete path back to the battery. What about these? No, these will not work. Current cannot flow here, current cannot flow here, current cannot flow here. It is blocked. How? By the open wire over here. Now, so we established the fact that anything in parallel is 12 volts. How is that, again, how is that associated with a circuit or a car 20 years later, 25 years later? Let's look. Here's your typical circuit of a parking lamp and a headlamp circuit or taillights. Aren't these in parallel? Are not these in parallel? Look at this. These are in parallel. Look at these. These are in the parallel. It looks different because of the way the manufacturer printed the schematic. Same thing applies. It could be 20 years later, 25 years later. It still could be in parallel. We don't want all the bulbs to go out if there's a problem in the wiring. We only want that one to go out. So 12 volts across here, 12 volts across here, 12, anywhere there's 12 volts. Okay? Now, so therefore, this schematic in this textbook which I had in school, like I mentioned various times, still appropriate to today's technology. Now, I want to introduce two things, as the viewer asked. And then we'll go into the relay, then we'll go back to the bad grounds. So then you'll understand exactly what I'm doing and what I'm trying to accomplish here. Now, there's 12 volts here, 12 volts over here. When these bulbs are lit, okay? When these bulbs are lit, regardless of their fog lamps, whatever their purposes are, if I go to 12, if I put a meter, doesn't matter what type of meter, a fluke meter, any type of meter, on one side is 12 volts. After the fuse, what do I mean by after? That means the one that's connected to the load. I consider this after. This is before the fuse, after the fuse. How much should I measure? I told you, and I tell you every single time, if that fuse is good, 12 volts. But in reality, when these are lit, they are drawing current from the battery. So in reality, you know what you're going to measure? You might measure 11.7, 11.6 volts, actually a little less than at this point. So if this is 11.7 or 11.6, what does that tell you? That tells me, as an electronic technician, even though 12 and 11.7, it's close enough to say it's 12 volts, because that's what we always do in automotive. But from a perspective of electronic troubleshooting and diagnostics, which I'm trying to teach, what happened to the 0.3 volts? Where did it land? If I'm at this point over here, and I'm measuring with the meter, 11.7, where did the rest of, how much is the difference? 0.3 volts. Even though it's so minimal and it's so small, why am I even paying attention to 0.3 volts? Why can't I just say, you know what? This is 11.7 volts. Fuse is good. So so what's the big deal? Instead of 12 volts, I'll get 11.7. They're still lit. Doesn't make it, no. That 11.7 volts tells me I lost 0.3 volts across where? What is the only component left from here to here to lose it on? The fuse. So in actuality, what am I losing? I'm losing 0.3 volts or 2 volts, 0.2 volts across the fuse. What does that tell you? As soon as I put my meter, regardless if it's from Harbor Freight, regardless if it's from Sears, regardless whatever type it is, and I measure 11.7 volts, that's important to me as electronics. That tells me current is flowing. That tells me one of these bulbs, two of these bulbs, three of these bulbs is pulling current. And what else does it tell me? That tells me there is a complete path to ground somehow in this. There might be one open wire over here, but somehow there is a complete path for current to flow, and that's why I lost 0.3 volts. That's the first thing that should come to your mind. Let's relate that to a modern schematic. Remember, this is just a textbook. This is just the foundation. Okay, let's go back now. Okay, you saw the schematic, I guess, a couple of videos ago. This is the best schematic that I found for beginners. And if you want to go to that, you can find it on the video on the channel, Joe Electronic Schematics for Auto. A relay that we went over so many times, right? I just said to you a fuse has 12 volts on one side, 12 volts after the fuse. If this is a relay, which side starts first? Always, this side starts first. It has to be energized first. Then this will be energized. Where is this going to? This is going to ground. I started the video. My first statement that I made was from a textbook. And I said a bad ground could be 1 ohm, 2 ohms, 3 ohms, 4 ohms. It'll change the voltage of the circuit. So, according to the viewer who asked me the question, how much should I measure if I put a voltmeter, and I have to put a voltmeter, I have no choice. It's not enough to just measure 12 volts over here and say, maybe the relay is good. You have to come to after the relay, put a voltmeter over here, and say, let me measure how much. Should I always measure 0 volts, always from here to ground? Let's say, instead of this wire, I drew resistance, okay? Let's say this is a resistor from here to ground. 4 ohms, 5 ohms, whatever. What's the problem with that? From the textbook, you can infer, you can derive a conclusion. And what's that conclusion? That conclusion is the more resistance that I'll have from here to here will give me what? A voltage drop. An unwanted voltage drop. An unwanted resistance. How do I get that from the textbook? Because a resistance, there should be no resistance from here to ground, regardless of the type of vehicle, regardless of the type of circuit, fuel pump, storm, regardless, 0 volts. Now, if I have 3 volts over here or 2 volts, that's too much. What does that mean? What does that tell you? That means from here to here, I have resistance increased. That's why I have a voltage drop. It's associated with Ohm's law, like we just discussed, but I don't want to get too technical with that, how I derive from that and all that. All you have to remember is voltage drop from here should be 0 volts. If I went up to 2-3 volts, unacceptable. That means that there's some resistance from here to here. That's point number 1. That's what we can derive from this circuit. We started off with a bad ground, a good ground, a bad ground. This is a bad ground. This resistor is now in the place of this wire. Bad ground, unwanted resistance. Let's go over here that we just talked about. The same thing applies to this. We cannot afford to have resistance here from here to ground. Other question, other one that I posed to you before, how much do you measure? And I said you measure across the fuse 0.3 volts. In reality, if you see the videos that I made, some of them, how to measure relays in the circuit in the car, I put the voltmeter on one side of the fuse, like we just said. The other side, I always tell you 12 volts. Again, to reiterate the point, to get over the point that I just made, in reality, I measure probably about 11.7, 11.6. And how much does that tell me? That tells me I'm losing some voltage across the fuse. The same point I just made in the textbook over 20 years ago from the school Lincoln Tech. The same point we can make today, and we could derive for any Asian vehicle, for any European vehicle, for you name it, Sonata, Fusion, any car. If there is a circuit, and there are multiple circuits with relays, right? I measure 11.7 volts. What does it tell you? It tells you current is flowing in this circuit. It tells you I'm losing about 0.3 volts. Again, is that important? If you're a real technician and you want to pick up on little details, it is. Again, what's the difference between 12 and 11.6? Close enough. I know the fuse is good. No, it tells me that current is flowing and there is a complete path from here to here. That's good. That's good. Because I want to make sure nothing is open in this line. Okay? Now, will it just suffice for me to just put the meter here and say, okay, if that's true, Joseph, you know what? So I measure 0.3 volts over here, so current is flowing. I don't have to go to the other side of the relay because you just told me that I'm measuring 0.3 volts or 0.2 volts across, so I have current flowing. No. You still have to measure from here to ground. How much should you measure? 0 volts across here to ground. How much will this, if this is 11.7 after the fuse, how much will I measure here? Same thing, 11.7. What does it tell you? It tells me current is flowing in this relay, in this coil, in this control side of the circuit. That tells me that there has to be a path, complete path to ground somehow. That's why I started this conversation or this video telling you the easy diagram I showed of the light bulbs, and now I'm advancing it to this circuit of modern day, how it is appropriate. So if I measure 12 volts here and I measure 11.7, and you'll see the meter, like I said on the videos on the channel, Joe Electronics Schematics for Auto, and you'll see exactly what I'm talking about, 11.7, 11.6. So I lost 0.3 volts. No, that's crucial. That tells you current is flowing. And I have to stress this point again and again and again, because many people don't pick up, especially mechanics from 40 years they're working. No, it tells you that this side of the circuit is working. Is this side working? We don't know yet. We don't know that yet until we measure here and here. But this is working so far. Just from that little a variation of 12 volts to 11.7, 11.6, that if this is not working, guess how much I'll measure? Probably 12 volts. So I measure 12 volts here, 12 volts over here. What does that tell you? The fuse is good, but it also tells me current is probably not flowing. Something might be open. So if you pay attention to these little details, and again, I'm getting probably a little too technical, but you'll see from the videos that I made on the channel, when you measure the fuel pump or when you measure the relay or any relay in those videos that you see that I measure it, you will see a small little difference on that fluke meter. And you'll say, oh, now I understand what he's referring to. So you pick up a little thing and it'll help you right away. Right away, because when you look at this relay, maybe the relay is open. Maybe the control side is open. Maybe there's no path back to ground. Boom, 12 volts here, 11.7, 11.6, 11.5, whatever it is. That tells me, so far this is good. Okay? Will it tell me that the ground is good? No. I still have to measure the ground. Make sure there is no unwanted increased resistance. Make sure I get about 0 volts. Because if this is 11.7 volts, I can still measure 2-3 volts from here to ground. Remember that. I hope this was informative, and I tried to explain it as simple, as basic as I can because of the questions that are being asked by the viewers, and they're very good technical questions. I really enjoy questions like that when it comes to deep questions like that. And so anyway, I know so they told me to go to an automotive school and to go to electronics school. Hey, keep up the good work. I hope this has been helpful to you. So remember this little point that I pointed out. If this was informative, please give me a like or subscribe. Thanks for watching. See you next time.